Hi, in this segment, I'm going to talk about an interesting property of pseudo-random functions. The property of interest is linear property. Okay, I would like to see whether for a randomly generated pseudo-random function, suppose I have 2 points x and y, k being the key. What can we say about f of x XOR with f of y? Is this equal to, I'm going to question this, right? F of k XOR of x and y. This property is satisfied, it will be very bad for cryptographic usage. I will talk about why it is bad later, but in this segment, I will only focus on this particular question. Okay, we already constructed a pseudo-random function f as follows in the previous segments. We made use of we made use of a one-way function. We took the one-way function based on number theory concepts, right? Based on Bloom-Shub generator, right? Bbs generator. You don't need to know about the generator at this point. We can treat it as a black box. So this is the algorithm we use to generate a pseudo-random sequence. Given a CDS, S could be your key. It was able to produce a long sequence of outputs. Okay, we made use of this Bloom-Shub generator for our pseudo-random generator, taking S as the secret key. We leveraged that to construct pseudo-random function. Okay, so under the hood, we made use of the Bbs generator to construct a pseudo-random function f. For a given key and an input x, it was able to give us some random output. Okay, we played with this f in the previous segments. We changed a bit of x, and we noticed that the output is significantly different. We also changed the bit of a k and looked at the output. We noticed that when a small change is happening in one of the inputs, x or k, we have significant output in the difference. Okay. Now we take it to the next level. Now, what happens if we do this? We pick x and y randomly, right? Two random numbers we pick from the set of all random numbers, and we call the pseudo-random function f, and we would like to know whether this property will be satisfied. Our intuition is telling us clearly that this wouldn't be the case, right? Because x and y are randomly picked, and f is supposed to be a strong pseudo-random function, cryptographically secure pseudo-random function. This should not be happening. So I would like to show you that for the generator that I constructed using the tree structure that we talked about. Let me draw the tree structure. We started with the root node, right? Root node becomes the key. The key is same as yes. Okay, we can replace yes by key. So we had a root node. This is our key. We call the generator, right? It gave us g of k. Remember, the g was doubling the length. So if we send in an n-bit number, it is giving us a 2n-bit number as output, right? That's the purpose of the generator from BBS logic, right? So given a key k of length n-bit, we will get out 2n bits, right? So what we do is we go into branching depending on the value of x. Okay, we model x also as an n-bit number. Okay, for simplicity, we assume the key length is same as the block length. Okay, we model like this, right? N-bit number, and we first call g of k. We get 2n-bit number because of the definition of g of n. This is how g is defined. We send in n-bit number, we get 2n-bit number. So we look at the value of x1. If x1 is 0, we take the left half of g of k, right? That's what we denote by g of k subscript 0. This is the left half. If xi is 0, we do this. If xi is 0, we take the left half. If xi is 1, we take the right half of the output coming from g. Okay, that's what we're going to do in this tree construction, right? So we decide whether the current xi bit is 0 or 1, starting from left, right? This is x1. If it is 0, we take z0 of k, right? The first half of the output of g. And then we take that as a seed for the next round, right? Okay, so we continue like this, say again 0 1, again 0 1, and the tree was, this becomes the seed now. So this node becomes the seed. We call G again, and then we take the left and right depending on the value of the x2, xn. So there will be n levels, right? This is the level level x. This corresponds to x1 decision making, right? This is used for x2 and so on. So that you have a large tree, and the leaf nodes give us the concrete value for our function f when we calling x, and when we call this with the key k and the x as inputs. Okay, this is what we learned in the previous segment, and I talked about it in detail. Okay, so now I'm going to instantiate this tree structure, right, under the hood for my Bbs generator. Let me revise this. Bbs generator is based on number theory concept. Okay, so we will treat that as a black box for now. But the pseudo-random function is, this is the pseudo-random function construction. Okay, this is how we construct the pseudo-random function. What I'm going to show to you is this part. F of k of x XOR with f of k of y is not equal to f of k x XOR with y for many x and y. Okay, this is what I'm going to explore with you. Okay, I hope it's clear. BBS is a black box for us. We send in some secret yes, we get out, if s is an n-bit number, we get out 2 n-bit. So it's doubling the input lengths. And we constructed the pseudo-random function f using this tree structure. Okay, and if this tree structure is not clear, I recommend you to watch the other video segments where I talked about it in detail. Okay, so let's do the demo now quickly. Create a key, say 128-bit key, and I'm going to make the block length also 128, the x, right? Okay, this is in bits. Okay, so I'm going to call this pseudo-random function f on 2 points x and y, right? First, I evaluate at point x and point y using the same key k, of course. And then I'm going to also evaluate at x XOR y. That's why you see XOR y here. And I'm asserting that it's nonlinear. Okay, f of k x XOR with f of ky is not equal to f of k XOR of x and y. Okay, that's what I'm asserting here. And I'm trying just for proof of concept 3 times, but you can increase it. If you don't see any error message, that means the assert is always true, right? As you can see, there's no error message. Let's introduce an error then. Okay, right away we get an error message. So there may be case that this is true, meaning this assertion is equal to is true, but it's a very negligible probability. Okay, very negligible in terms of cryptographic strengths. So no need to worry so much about this. If we assume that the function f is properly constructed, we will always have the assertion not equal to in practice. Okay, so we can increase the number of attempts. Let's try that. Let's reduce the key size for our demo purpose to 64-bit key, right? And let's generate 10 random numbers. Okay, and let's keep the demo simple now. So it's trying 10 different attempts, meaning 10 different x and y's are generated. See, all of them satisfy this assertion. So it's not linear. Now we can dive a little bit deeper into the function f, right, which takes the key and x as input and the block length. Block length is the x length, okay, in terms of bits. All we are doing is we are repeatedly calling the Bloom generator under the hood, the function g that I talked about on the whiteboard. And depending on whether the current xi bit is 1 or 0, if it is 0, we take the left half of the output that we got from the generator, right? Otherwise, we take the right half. And we repeat this. That's basically what we did here. Okay, the generator G itself is based on the number theory concept of quadratic residues and computational problems related to factoring. So we don't need to go into the details of how G is designed. But the fun part is that the tree structure that we talked about in the previous segment it has this nice property that the function f is actually indeed a pseudo-random. We tried with many interesting things. We changed a little bit of x. We saw significant output in f. We now also asserted that the pseudo-random function is nonlinear. Okay. In the next segment, I will show to you that the nonlinear is important from a cryptographic perspective, because This is related to the theory of computation problem. If we have a set of equations, nonlinear equations in binary, meaning mod 2, we don't know how to solve such equations in general. There may be easy cases that we can solve, but if we have lots of variables like 128-bit or 64-bit key, trying all possibilities, 64-bit may be possible easily, but if you take, say, 128-bit, you will get an enormous number of equations to solve to break crypto systems. Okay, I'll talk about that later in detail. But at this point, it's important to know that pseudo-random functions are nonlinear. Okay, that's an important property we need. All right, that's all. Thank you very much for your attention.